Hi, everyone. My name is Michael, and welcome to Multi-Platform Functional Architecture with Oolong. This is a follow-up session to one I presented last year, in which I spoke about functional architecture at a high level. And today I'm going to talk about a specific functional architecture pattern for managing user interfaces. But first, let's do a recap of functional architecture. In my last session, I talked about an issue that you have likely encountered too. The term feature parity is something that is core to mobile development, and different mobile teams are often playing catch up with each other in terms of uniformity and consistency of features. I suggested that the root of this problem is that both teams are trying to solve the same problems, but in different code bases. For each platform you target, there's likely a large amount of duplicated effort. My proposed solution to this was to take these multiple code bases and teams and combine them into one core team, writing shared Kotlin code with platform specialists who write platform-specific code to host the core application. So I broke down each term in order, starting with multi-platform. And by multi-platform, I simply meant Kotlin multi-platform, which is a tool that allows you to write common Kotlin code that compiles to multiple targets. And this is what enables our core team to work together in a common code base with a common language. Next, we took a look at the functional aspect. And by functional, I mean functional programming. This one slide describes the entirety of lambda calculus, which is a mathematical system for expressing computation. And this is what functional programming is rooted in. So by using abstraction and composition, we can use something as simple as the syntax, and we can create complex programs like this FizzBuzz program. In lambda calculus, only pure functions are allowed, and functional programmers try to keep functions pure as much as possible. Pure functions have some qualities that make them really attractive. Pure functions are deterministic. This means that for any input to a pure function, the output will always be the same. And pure functions are free of side effects. This means that when you call a pure function, you can be sure that nothing is affected outside of the scope of that function. Because of these intentional limitations, functional programming relies heavily on abstraction and composition. Finally, I talked about architecture. And when I think of architecture, I focus mainly on boundaries. And in functional architecture, I consider the primary boundary to be that between pure and impure code. However, a program would be useless or even impossible without some impure code. Otherwise, how would we print to the screen or write to disk or perform network operations? So we need a way to cross that boundary. And we do this by opening up ports into the pure code and creating adapters so that impure code can fit into those ports. This architectural style goes by a few names: ports and adapters, onion architecture, hexagonal architecture. But by using this boundary of pure and impure code, functional architecture emerges naturally. Just like functional programming relies on abstraction and composition, so does functional architecture. In the last session, I left off with a few important concepts: purity, boundaries, and composition. And in this session, we'll visit each of these again in a specific context. When an architecture style is applied to a specific context, we call that an architecture pattern. And today we're going to look at an architecture pattern for managing user interfaces called Model View Update, or MVU for short. Specifically, we're going to look at how this pattern is applied using Oolong, which is an MVU library written in Kotlin multi-platform. Oolong is inspired by the Elm language and the Elm architecture, where the pattern originated. But Oolong is different in that it is adapted to run everywhere, not just web browsers. As a simple diagram, model view update looks like this: a unidirectional loop between the user and the program. Our application state is contained in a model. To present this model to a user, it's passed to a view function. The view function then returns a data structure which represents the properties that you want rendered. The properties are passed to a rendering function specific to a platform, and this is where the platform specialists adapt the core program to fit into their platform. As a result of UI actions like button clicks or text entry, messages are sent back to the core application. Those messages are given to an update function whose job it is to interpret the message and return a new model. This completes the unidirectional loop between a user and a program. However, not all messages come from a user. Some messages are a result of a network request, a database read, or other side effects. So to handle this, the update function also returns another function which describes a side effect to be executed. The side effect is executed in a different context by an effect runner inside the Oolong runtime. And effects call back into the main MVU loop by dispatching messages, which are then passed into the update function. And this completes the unidirectional loop for side effects, and now we can see the complete MVU architecture. There's an article by Andre Staltz, which he talks about all the different unidirectional UI architectures, and he describes MVU as a fractal architecture. That means it's fractal because the subcomponents are structured in the same way as the whole is. And in model view update, this is achieved through composition. So let's write a sample app to see concrete examples of all these concepts. We're going to write a counter. At first, it will be very simple, and slowly we will add features to demonstrate concepts like boundaries and composition. But to start, we're going to focus on purity. Again, here's the full MVU diagram, and we're going to focus on this pure loop. First, let's focus on the data structures being passed around. The model is a state of our application. These are the nouns of the system. For this application, it's quite simple. It's just an integer for the current count. Next, let's look at the messages, which are the verbs of our system. What actions can we take on those nouns? And currently, there are only two actions we can take. First, we can increment the count, and conversely, we can decrement the count. You'll notice that these messages are in a sealed class, which allows them to be enumerated. And later on, we'll see why this is an important quality to have. Lastly, we have the props, and this is what we pass to the platform to be rendered. In our UI, we want to show the count. We want to provide a function to be called when the increment button is clicked. And we want to provide a function to be called when the decrement button is clicked. Now, these functions are passed an instance of dispatch, which allows us to send a message. And dispatch is simply a type alias for a function which receives a message and returns unit. When this function is called, the runtime will send the message to the update function. So now that we've defined the data structures, let's take a look at the functions that consume and produce these data structures. You might have noticed something missing in the MVU diagram. How do we begin the unidirectional loop? And this is achieved by providing an initialization function. And this function takes no arguments and returns the initial state of the app as a model. And we also pair that initial state with an effect. Our initial state for this counter is a model with a count of 0. And we don't want to run any side effects yet. So we return an empty effect by calling this none function, which is included with Oolong. The update function takes 2 arguments, which are the message that was dispatched and the current model. Once again, we return the next model and any side effects that we want to be run. We use a when expression to match on all the different instances of our sealed message class. And because the update function is returning the result of this when expression, the compiler will require you to handle every possible case because it is exhaustive. And IntelliJ, if you're using IntelliJ or Android Studio, will also give you completion actions to fill in the rest of the cases, which just makes this a really nice thing to have. So the first case we handle is the increment message. And whenever we receive this increment message, we return a copy of the current model with the count incremented by 1. But why aren't we just incrementing or reassigning the count of the model instead of returning a new model? Well, this is another concept used in functional programming called immutability. So by limiting when and where data can be changed, we can make data much more predictable and safe. So under the hood, Oolong handles the state mutation, and all we need to be concerned about is how a model should be affected by a message. And when this update function returns a new model under the hood, Oolong will reassign the current model. Similarly, we handle the decrement message, the instance of message, by returning a copy of the model with the count decremented by 1. Along with this new model, we need to return an effect. And again, here we are returning an effect of none. Finally, we get to the view function, which transforms the current model into view properties. So we return a new instance of props with the current count of the model assigned to the props count, an increment function which calls the provided dispatch function with an increment message, and a decrement function which calls the provided dispatch function with the decrement message. So now we have all these functions. We can initialize our new Oolong runtime using the runtime function. The host platform creates this runtime instance and handles rendering. These functions we just defined are the pure part of our code. And then we have a render function, which is one of the boundaries into the impure code. This render function is given the props that were returned by the view function, and the runtime also gives it the latest dispatch function, which allows messages to be sent to the update function. So in the sample app, we're going to use Jetpack Compose to declaratively render these props. We have a composable function called counter, to which we pass view properties and the dispatch function. And here's our composable counter function, which takes a props and a dispatch as arguments. And we create an outlined button with a drop-down arrow. And in the onClick listener, we call props.decrement, passing in dispatch. Next, we create a text and set the value to be props.count. Lastly, we create the increment button with an up arrow icon. And in the onClick listener, we call props.increment with dispatch. A major advantage of both functional architecture and functional UI architecture is that it creates highly testable code. In MVU, we can test that messages result in the correct model. We can test that the correct effects are returned from an init and update. we can also move a lot of UI testing into unit tests because our UI is now represented as a data structure. So first, let's test the result of the init function. We arrange the test by expecting that it will return a model with a count of 0. We act by calling the init function, and we split out the model and effect using destructuring syntax. And finally, we assert that the expected model and actual model are equal. Next, we test that the update function handles the increment messages correctly. To test the increment message, we arrange our expected model, given a message of increment and an initial model of 0 with count of 0. And here we expect a model with count of 1 to be returned given an increment message and model with a count of 0. We act on the message and model using the update function and assert that the expected model and the actual model are equal. We also test that the update function handles decrement messages correctly. So similarly for decrement messages, we arrange, we act using update, and we assert that the expected model and the actual model are equal. Lastly, we can test that the view function transforms models into view properties as we expect. We arrange our model and expected count property. We act on the model using the view function to return view properties. And we can assert that the view count is equal to the model count. We can also test that our UI callbacks send the correct messages. So we arrange our view properties. We act on the increment callback by calling it with a trailing lambda, which would be a dispatch function. And a dispatch function, if you recall, takes a message. So we have here a message called given to dispatch by the increment function. And we can assert that the message it dispatches is the increment message. And once again, for decrement callbacks, we arrange the properties, act on the decrement callback with a faked dispatch function, and assert that the decrement function was dispatched. So let's add another feature to the counter app. Currently, if you close the app and open it back up, you'll lose the current count. And this is because we aren't persisting the count yet. But let's see how we can use ports and adapters and effects to cross this boundary of purity. So to start, let's create two abstractions. First, we want to create a type called getCount, which is a 0-argument function that returns an integer. And we'll use this to an instance of this abstraction to get the persisted count. And next we create a type called putCount. And this is a function which takes an integer as its argument and returns unit. And we'll use an instance of this type to persist the count. Now that we have these abstractions for persistence, let's create implementations. We'll create a class that takes a context as its argument. This is an Android implementation. And from that context, we can obtain an instance of shared preferences to use as our persistence mechanism. We'll create a value with type of getCount that we just defined. And when this getCount value is invoked, we return the stored count from shared preferences. Next, we create a value with type putCount. And when putCount is invoked, we save the count to shared preferences and implicitly return unit. So as you can see, we've defined ports as type aliased functions and adapters as instances of those functions. So these ports and adapters we just created run side effects by persisting the count to disk. But how do we ensure that our pure code remains pure while executing these effects? And we do this using a concept called managed effects. So instead of running side effects directly, we package these effects to be executed in an impure context. Again, looking at our MVU diagram, this is our effect loop. And side effects are run by returning a packaged effect from the update function. So let's take a look at the definition of effect to understand it better. Effect is just a type alias for a function that receives a dispatch and returns anything. So we give you a dispatch so you can call back with a message into the main interaction loop. The effect runner ignores the return value, but it allows anything to be returned just so we don't restrict the body of the function to a specific return type. It's just for a nicer API. This function is also suspending because effects are executed in a coroutine. And to give you control over the context in which your effect is run, the function has a receiver of coroutine scope. So now let's package our ports and adapters into managed effects. Here we've defined a function to create effects for getCount. This function receives an instance of getCount and returns an effect. And we create this effect using this effect builder function, which is just nice for helping you with types. When the effect is executed, it will get the persisted count by calling the supplied instance of getCount and dispatch a message of setCount back to the update function, to the main runtime, with the value that we just obtained. The putCount effect receives an instance of putCount, and it returns another function. This function receives an integer that we want to persist, and it returns an effect to persist the count whenever this effect is executed. And so inside the effect, we'll persist the account by invoking the injected instance of putCount with the count that was passed to this outer function. So let's look again at the initialization function. When the counter is initialized, we'll want to load the persisted count and set it in the model, but we don't have an instance of getCount in this function currently. So we can turn this function into a factory, which injects an instance of getCount into the init function. So in the body of the outer function, we return the original init function, but here again, we're still returning an empty effect from the init function. So instead, we're going to return an effect by calling the getCount effect function with the injected instance of getCount. We don't have a message called setCount yet, so let's create it. And it's just a class with a property of count. And now we run into a compiler error in the update function. And this is why the sealed class and exhaustive messages are nice. Since the when expression for message is exhaustive, it recognizes that it doesn't handle this new instance of message called setCount. So let's add this case for the setCount message. And when this message is dispatched, we set the count of the model with the current value captured by the setCount message. And just as we created a factory function out of the init function, we'll do the same with the update function by wrapping it in an outer function. The factory function receives an instance of putCount and uses the putCount effect function to create an effect from the injected instance. So now instead of returning none for all updates, we want to persist the count on every update. And so we'll return an effect which puts the current count whenever the effect is executed. And now we have some more compiler errors, this time in creating the runtime. init is no longer an init function, but rather it's an init factory function. So to get an init function from this factory, we invoke the factory with an instance of getCount. And remember that getCount is the port, and the instance that we just injected here is the adapter that we created in Android. Also, update is no longer an update function, but rather an update factory. So to get an update function, we invoke the factory with an instance of putCount. Remember that the runtime is hosted inside the platform, and these injected adapters are also likely to be specific to the host platform, though not necessarily. You might have different adapters for each platform you write. So let's write a test to ensure that the initial effect dispatches a setCount message. We arrange the test with a faked instance of getCount that just returns 0, and then our expected results. We act by running the effect in a blocking coroutine, and we assert that the message dispatched is equal to what we expect, which was a setCount with 0. We also want to test that the update function, the update effect invokes the injected instance of putCount. So we arrange the test with expected values. We act by running the effect, and we assert that the faked instance of putCount receives the expected message. Finally, let's have a look at composition by allowing the user to have multiple counters. And we'll do this by creating a new MVU component that delegates to the one we just created. So each individual row will have the same features of persistence and incrementing, decrementing as the component we just created. Remember that MVU architecture is fractal, meaning that subcomponents are structured in the same way as the whole is. And this is achieved through composition. So let's take a look at a general example of a parent-child component relationship. Here we have a child component. It has a model, messages, props, and an init function, an update function, and a view function. And these are all the fractal parts of an empty MVU architecture. So the parent component will also have these same pieces. The parent model is a composition of the child model. So it has an instance of child model as a property. The parent message is also a composition of the child message. So here we have an instance of message called child message that holds an instance of this delegated message class. And the props is a composition of child props. So properties has, or props has a property called child, which is an instance of child props. The parent init function delegates to the child init function to compose the initial state and any side effects that the child component wants to run. And the parent update function delegates to the child update function again to get the child's model and effects to run and compose that with itself. And the parent view function delegates to the child view function to receive its properties based on the child view that is encapsulated with the parent model. So now that we've demonstrated this composition generally, let's apply this to our new counter design. First, we'll define a model. And this model has a counters property, which is simply a map of IDs to counter models. So each ID represents, each mapping of ID to counter model represents a row. And so we can select on ID to update those. Next, we create our messages. So we have messages like set counts, so we can add a counter, we can remove a counter. But the composition / delegation piece here is that we have a message called counter message, which holds an ID, and so that we can look it up in the parent model, and a message so that we can delegate that child counter message from the parent to the child. We'll need a props class. And so here we have a list of counter rows, also a function to add a counter. And a counter row is defined inside the props class, which is composed with the child counter props, and then also a remove counter function so that we can remove the counter if we want. For the sake of time, we're just going to cover the data structures because there can be a bit of boilerplate, and there's a lot of other things happening in this parent component that adds some complexity to the slides. So just note that the function delegation we saw for the general example also applies here to this sample app. The complete source is up on GitHub if you want to see details of these functions, though. So what have we learned here today? Functional architecture favors purity, boundaries, and composition. Architecture patterns are architecture styles within a context. And model view update is the functional architecture style applied to the context of UI management. MVU is a unidirectional UI architecture which keeps code pure by managing side effects, makes testing straightforward and easy, and is highly fractal and compositional. So if you want to learn more, please visit oolong-kt.org. This is all prior art from Elm, and you can learn much more by visiting the Elm guide. And if you want to see, again, if you want to see the complete code for these samples, including all the UI rendering and Jetpack Compose, you can check out the GitHub repository that I created for this session. So thank you for watching, and I'll take questions now. All right, so the first question is, how is MVU different from MVI or Redux? So I'll start with Redux. Redux actually lists MVU as prior art, so it's very similar. The ways in which it differs, and the reasons I prefer MVU over Redux, having used both, MVU models effects in the update function, as we just saw, whereas Redux manages effects through middleware, which is included at the top level. So to do side effects, you really can't have this fractal architecture because side effects don't happen inside of the architecture. It happens when you create an instance of Redux. Additionally, the way Redux is implemented, messages are not exhaustive. If you take like a verbatim implementation from redux.js, the messages are not statically typed. They can be anything. So from that perspective, it's not as safe as MVU. The ways it differs from MVI. So Andre Staltz, who I mentioned earlier, wrote this article about all these unidirectional architectures. He's also the creator of Cycle.js, which I think is where MVI originated. And he describes the difference from these two, MVU and MVI, as MVI is reactive and uses observable reactive streams, whereas MVU is more functional and doesn't rely on this monad of an observable. So we also at a prior company created an implementation of MVI using RxJava and what we found was that it was fairly difficult to reason about and understand the flow of data through all these streams and combinations. So that's one reason I prefer MVU over Redux or over MVI. Can you talk about the benefits and problems with this approach for larger applications? So I demonstrated composition in this example, composing the subcomponent in a larger screen. This style of composition can have a lot of boilerplate, as we saw, and should be limited to certain scenarios. And that scenario that I think it should be limited to, and like the advice I've seen in the Elm community, is for screen switching. So you can have a root component which uses the style of composition and delegation to switch between screens. That is the main pain point that I've encountered using MVU. And so I would recommend to use functions for composition as much as possible over data structures. Benefits, all your code is in one pure context, and things that change together are co-located, and it's very easy to refactor. Next question. How easy is it to move from MVU to MVU from MVP or MVVM? Have you migrated from such architectures? Also, is there room for use cases adopted from clean architecture? Yeah, so I'll start with the use cases question. The ports and adapters example that I showed using like a type alias interface and like a value implementation, that's just like a functional way to do use cases. I got started like down the architecture path of learning with clean architecture. And one thing that I took away from clean architecture is that there's a lot of ceremony and structure, and use cases is an example of that. But they are basically the same as ports and adapters. So if you like all that structure and ceremony, that's perfectly fine. You can use use cases as your like boundary crossing mechanism. You would just run that inside of an effect. So moving from MVU to MVP, again, this is this type of architecture, because it's fractal, that also means it's like you can be very isolated. So you can start moving pieces of your architecture, a screen, a component, to MVU from anything else. And there are plenty of examples of this in the Elm community, and it's like success stories of we want to adopt Elm. but we just want to try it out and see if it's for us. So we just change one component in a screen to use Elm, and then move on from there. So I would say that yes, it's fairly simple to migrate to MVU. Are you still able to use view models with this architecture? And if yes, where do they fit in? Also, how does this architecture respond to lifecycle events and configuration changes? So again, we can learn some things from Elm. When Elm initially came out, there was one runtime per screen. And so every time you refresh or went to a new HTML page, it would spin up a new runtime, which would last for the life cycle of that page. And now it's more common to use single page apps. So think of what I described earlier as having like a root component, and then each page is delegated to and has its own component. So the first example, I would make an analogy to view models. So a view model has like a similar life cycle to like a web page. It's hosted in activity, and you can move between view models, and you can have a runtime per view model, and manage or use Oolong that way. Similar to how Elm has SPAs, single page applications, is what I like to do is to host the runtime inside the application process. And this is nice. Both ways are nice. But this is nice because there's just one entry point, and I can use compose to destructure the properties and decompose that from there. If it's in the application or in a view model, like lifecycle events, you can send messages from created from lifecycle events if you want, but because the runtime stays around, especially in the case of hosting in the application, you really just need to attach back onto the runtime and rebuild your UI based on the latest model. And there's examples of this in the code base that I've of the application instance style in the code base that I uploaded. Next question from David. What if you need to take actions based on comparing the previous set of data with the new one? So that is what the update function does. The update function receives as arguments the message that was dispatched in the previous model, which is the previous set of data, and it's your job to create a new model to transition to. I suppose if you wanted to hold data like previous data further back from models prior to that, even you would build that into your model as like a growing list of those previous values, and using like this concept, you can also do something called time traveling, which is holding previous states and the messages that it took to get to those states, and you can scrub back and forth between those different models and do some time traveling. This last question, how would you compare MVU with the approach Pardo took at MVI core? I'm not very familiar with Pardo's MVI core, but I think I already talked a little bit about the differences between MVU and MVI. As the inventor of MVI describes, or the first instance I can find of MVI is Andre Staltz's Cycle.js. It's really just like an implementation detail. The mechanisms you want to use to create this loop. One is reactive. MVI is reactive, and MVU is one reuses reactive streams, and MVU reacts to messages and dispatches to functions. I think that's the primary difference. It looks like that is all for questions. So thanks, everyone.